Noise, a chip killer. Concern is growing on complex designs where there are few dedicated tools to help find and deal with it. Noise has always been important to communication experts, but it quickly became an issue that every semiconductor designer has to contend with. Some chips already have been compromised. Noise can be defined as any deviation from the ideal that can impact intended functionality. When it comes to semiconductors, that could mean that our ability to reliably extract a signal value at the intended time or for voltage at a device to remain constant enough to be able to reliably create or sense a signal. In the communication space, noise is usually analyzed using an eye diagram. These diagrammatically show if the noise encroaches into the region defined for reliable signal extraction. Noise is in two dimensions, amplitude and phase. Phase noise comes about because of changes time in signals, particularly clock. Amplitude noise also can impact time and causing clock edges to move out of phase. Jitter. Noise injection comes from many sources at the device level. It starts with bias, temperature, instant instability, and flicker noise. But the noise sources are the growing of concern are orders of magnitude large in terms of their ability to compromise large portion of the design. As semiconductor technology scales below 7 nanometer, packaging becomes more complex. Power delivers noise has a major challenge, said Mohammed Hassan, 3D IC solutions engineer at Siemens EDA. Lower supply voltages, higher current densities, and denser interconnects increase IR draw. Inductive noise, DI over TD, and a power distribution network, PDN, discontinuous across stack dies. If not properly managed, dynamic voltage noise can reach to 5% to 10% of the nominal VDD. Managing noise has become one of the most critical and persistent challenges in modern semiconductor design. With the supply voltage shrink toward 1 volt and transistor densities continuing to increase, traditional design margins that once observed these electrical variations are all but gone, said Charlene Wan, Vice President of Branding, Marketing, and Investor Relations at Ambic. If minor fluctuations that were once inconsequential can now jeopardize performance or reliability. Power and signal integrity. In some cases, the problems are not new, but the context around them has changed. Signal integrity has been done the system side for over 30 years, says John Park, Product Management Group Director in the Custom IC and PCB Group at Cadence. We have advanced three-dimensional electromagnetic field solvers that are gonna extract very accurate S parameters of a channel and allows you to model that. However, if you are a die designer, that whole concept may be new unless you do analog. There is a convergence of what we historically did on the die side and what we've historically done on the system side. Leading edge chips today are consuming vast amount of power, and that is creating problems. The noise is an analog layer on the top of a digital design, said Mark Sweeney, Director of Product Marketing and ANSYS, part of Synopsys. The power line is meant to be perfectly stable, but it isn't. And that is power noise. Digital blocks often have intense bursts of action that impact the power supply. For analog designs or more sensitive regions of digital designs, you need the power to be more stable, so they have separate power lines. This creates other problems. Currently, in a complex SoC, you have 20 or 30 voltage domains, but only 2 or 3 of them are high current domains, said Andy Anick, head of Department of Efficient Electronics at Fraunhofer IIS Engineering of Adaptive System Division. There is a core voltage and maybe 1 or 2 IO voltages with a high current. Then you have 10 or 20 voltage domains that comes microamps only used to standardize something, such as a PLL. You have to reduce the noise of these to the lowest level, but with advanced packaging, we bring all the interconnects much closer to each other, and we get more crosstalk. The problem is not the absolute level of noise, it is that we have more choice on all supply nets, including the critical ones. We can't avoid it as we get them closer to each other. In total, more noise, more coupling, and that can introduce new problems. Some of these problems are becoming more apparent with advanced packaging. In analog and mixed signal designs such as DDR5s or HBM memory interfaces, IR drop can have particularly severe consequences, said Takeo Tomine, principal product manager and ANSYS, part of Synopsys. For example, in a DDR interface, localized IR drop in termination or driver circuitry can degrade signal swing, resulting eye closure and bit errors. Similarly, in HBM designs, where multiple high-speed I/O channels operate in parallel, even minor voltage dips can disrupt timing margins and cause data corruption or synchronization failures. Other system problems are also migrating inside the package. When you have a system with multiple elements on it, such as the case with a PCB, and if you have one chip being active, then a different chip being active, then back to the first, you can get power oscillations build up, said Ansi Swinen. There are resonant frequencies in the power distribution network, and if you draw power at the right frequencies, you can get these oscillations that build. These are low frequency oscillations. This did not happen with monolithic devices. These issues become more challenging as package sizes grow. When you start getting into interposer with long traces off to other die, errors can very much becoming an issue, said Joe Davis, Senior Director of Product Management at Siemens Digital Industry Software. You do have resonances. You start to have the same signal integrity issues in 3D IC that you have with the traditional package, because you're talking about shorter things, shorter traces than wires, and less of an impact. But these things are getting so large today. When you look at the roadmap for the foundries and systems that they are planning to put together with hundreds of dies, errors, seals becomes a significant impact. It's not just data center designs that are impacted. For ultra-low chips operating near threat voltage, such as those designed for wearables and IoT edge devices, The problem is magnified, said Ambikuan. These SoCs trade voltage margin for energy efficiency, which means that they are inherently more susceptible to drops, jitter, and crosstalk. Multiphysics world. Multiphysics problems have become a commonplace. From a packaging perspective, advanced platforms such as 2.5D or 3D integration, fan-out, and least distribution line interposers introduce new challenges, said Rogelia Baker, field CTO for package technologies at Lapidus Design Solutions. Analog blocks are vulnerable to power integrity issues, thermal gradients, and inter-die crosstalk, all of which can degrade performance. System-in-package SiP designs combine RF, analog and digital components, which further complicate verification, require multi-physics simulations that account for electromagnetic interference, thermal behavior, and signal integrity. What is are some of electromagnetic coupling problems? Digital systems have interesting noise problems, said Nilesh Kamdar, General Manager, Design Verification Business Unit at Keysight Technology. They are really easy noise problems compared to microwave or RF systems. As we go higher and higher in frequencies, everything is noise. Everything is either impacted you positively or negatively. But the high frequency problems mean a small piece of package, a small piece of connection can be an antenna. It can leak signals from that, if not properly designed, impact the chip next to the first one. So this should not have come as a surprise. Mo Faisal, Movilius CEO, predicted this 7 years ago when he said, you can take a chip and put wire on top of it, literally on top of it, and hook that up to a scope, and you will see noise at the frequency aligned with what it's switching at. If wire can detect it, so can a 3D die stack. This is a system level concern, and you have to find ways to spread that noise, not have everything stacked up at the same frequency. There will be EM radiation that will go from one device to the other. This is where system techniques such as spread spectrum come into play and allows you to spread out the noise so that it does not interfere. Additional problems that are only just being better understood. You can take a 5G, 6G as type of complex chip and our package system and assume that it works based on past experience. So the Keysight come down. Now we are getting into a world of multi-physics problem. Electromagnetic effects are one of the problems. Power leakage can be another problem. Thermal effect are another problem. The interesting thing is that three of these interact with each other. There is a problem where at a higher temperature and the electromagnetics change, or the impact of the higher power causes a thermal impact. All of these things work against you. Now you're trying to analyze a multi-physics problem that you previously could ignore because systems were far away and aren't really interacting that much. Now you absolutely have to handle them. This is a brave new world for us, where everything is multi-physics. As we go to denser technologies, like chiplet, and higher frequencies like millimeter wave, we have to manage this in a different way. Some new effects are impacting existing problems. As customers are pushing the frequency higher, they want to have better modeling for their clock jitter and clock uncertainty. Said Manoj Palapati, senior staff, product manager, and synopsis. These are effects that have always been present in the design, and the customer set up some margins to counter these effects. But now, aging has become a concern, and people need to know both fresh clock jitter and aged clock jitter. 2 years down the road, how does clock structures behave? Is there a more distortion of the duty cycles or close? Does jitter vary? Analysis. Noise is placing an increasing burden on verification. Circuits, such as HBM, bring together deeply intertwined analog and digital domains, making verification both broader in scope and more mission critical, said Karthik Connery, principal product manager at Synopsys. Regression suits now encompass thousands of tests, require not just functional correctness but also high accuracy across the process corners, noise conditions, and timing scenarios. The challenge is acute. You need the precision of analog verification without compromising the speed required for digital scale regression. The impact is real, too. SoCs with AMS content typically have first-time success rate 10% to 15% lower than a digital-only counterparts, said Rapidus Baker. This gap is often due to the insufficient core case coverage in adequate modeling and integrated with issues like power domain conflict and substrate noise. Analysis methodologies can combine static and dynamic IR drop simulations, electrothermal PDM modeling, and on-die voltage sensors to capture the transition drops and resonant behavior across the frequency ranges. Mitigating noise and its impact can be done at the silicon package or broader level, said Jim Hassan. At the silicon level, wider power layers, more wires, decoupling capacitors, as well as global optimization strategies such as current-aware floor planning and adaptive voltage scaling can be employed. At the package or board level, designers can utilize hierarchy coupling, die packaging, PCB, and low inductance power ground planes, optimized PDN impedance, and placement of high-efficiency VRMs near the load. Model verification has become much more important. I see a lot of time and effort being spent on model verification, and it is not done. Then your entire foundation is wrong, said Satishi Balasubramanian, head of product management and marketing for AMS at Siemens. And your verification, you suddenly see that the PLL has a lot of clock jitter, or PLL is not really coming up to the clock that you wanted. That's quite a bit nuance going on there. Model verification has become a big pain point. Perhaps the biggest issue that many noise failures fall into the category of silent data errors, where the root cause cannot be identified as extremely difficult to produce. In low-power devices, this failure may not be manifest as a system crash, said one. Instead, they may be seen as a reliable drift, a sensor miscount, a missed Bluetooth packet, or excess current draw leading to reduced battery life. Impaction teams. These are not just technical problems. They present organizational challenges as well. We need a new understanding about how much noise can be accepted, said Fraunhofer Heinrich. With chiplets and advanced packaging, we will get more questions. On the power side, we need more simulation to avoid IR drops, especially under different workload. This is a big problem Because if we integrated everything closer to each other, we start to see problems with overlapping domains. So the engineers separate everything into domains. We have the power domain. The power domain has its own models, and they are able to solve the problems. Now we are bringing everything closer to each other. And we have much more interaction. It means that engineers have to work together, but they are not taking the same language. Everyone has to learn new skills. As a digital IC designer, never in the past did think I needed a 3D electromagnetic solver to figure out what's going on. The Cadence Sparks. Now you do. I'm a packaging designer. I've never knew I needed to do formal DRC. Well, now you do. Although the convergence of system design tools and expertise and die design tools and expertise. We were talking digital obviously on the analog of LF side of things. They are familiar with the electromagnetics. A lot of what we focus on is how we integrate these flows so you don't have to jump over a 10-foot wall to get in between these tools that you need to use in the flow. Possible solutions. Noise can be managed using existing tools. At the front end, we can influence noise indirectly through the RTL design choices such as activity balancing, clock gating, and power domain control, said William Wang, CEO of Chip Agent. But the real leverage for minimizing IR drop and power integrity noise lies in the back end, where power grid design, decoupling strategies, and package layout determine the actual noise behavior. Looking ahead, AI agent could play a major role in the backend optimizing by autonomously analyzing EM, IR, simulations, learning from a past sign-off data, and suggesting the layout of the decap replacement environment to reduce the droop hotspots and optimize power distribution efficiency across chip and package levels. As problems get worse, more time and effort is spent on looking at long-time solutions. One area under consideration is increased adoption of on-chip voltage regulators. The bottleneck for integrated voltage regulators is developing the magnetics that will allow you to integrate those magnetic components inside the package. Said Luca Vasali, Customer Application Engineering Director, said Empower Semiconductor, the switching regulators needs inductors to operate efficiently, and those inductors need to store energy and be as efficient as possible, so they do not expect too much power. To make them small, you have to increase the switching frequency of converter and still maintain the very high efficiency despite the smaller size. There are downsides. It means additional rate. That means additional cost, said Heineck. Then it's not necessary yet, because you have to be able to by designing your package the right way to avoid critical surprise from getting noise from the other signals using separate one shielding. But by using an internal voltage regulator, maybe this avoids the complex simulation, even if you are bringing the noise signals on the fly, and it is internally regulated, and you just can be quite sure that a PLL, for example, gets a noiseless singlet. Maybe this is a technical solution to avoid this complex simulation, because you solved it in a different way. The old way is to avoid noise on the supply. Now we have an internal filter that filters out the noise, but you only adopt new approaches if they really need to, because in the beginning it brings uncertainties, and something else may go wrong. Unfortunately, it merely comes down to tightening the engineering discipline. No design can eliminate noise, but it can mitigate it through the careful architecture and implementation. Step 1. Your mindset matters. Treating chip, package, and a system as integrated PDM design challenge will help build less noise chips from the start. The trend toward heterogeneous integration, denser package, and near threshold computing will only make noise noisier and more complex to manage. For ultra-low power systems, each extra week or month to battery life saved by keeping noise under control. Okay, today I read this article, Noise, a Chip Killer. Thank you for your time. See you next time.